So our next speaker is William Dupont, or Dupont, as Paul Albert would pronounce it. Sorry. William is a PhD in 1977, and my web search revealed that he's currently a professor of biostatistics at Vanderbilt, and I think he's been all his career at Vanderbilt. So
it's my first job.
Yeah. So stability has to count for something as well, I would say. So William, thanks for coming.
Thank you. So, first challenge is how in the world do I get the slides to work? But anyway, it's a real honor and pleasure to be here to help in celebrating Chuck's first 50 years. The talk that I'm going to be giving is somehow particularly appropriate in that it was written by 3 statistical apostates who were profoundly influenced in their views on the foundations of statistical inference by Chuck as well as Richard Royal, and okay. But at any rate, this particular paper, and again, all 3 of us are alumni of this department. Oops.
Stay at the podium so maybe that might look this.
Okay. What I would like to talk about is the analysis of 2x2 tables. Many of the examples that are given concerning the foundations of statistical inference are what might be called toy examples. They're helpful for illustrating principles, but they don't really. They're never things that you would actually do in real life. In contrast, the 2x2 table is something that comes up all the time, where here we have fixed numbers of subjects who receive either treatments 1 or 2, and y1 and y2 are the respective number of successes, and y plus is the marginal total of successes. And for any given table, there's a wide variety of p-values that different methods will calculate. To my knowledge, there are at least 45 different publications, often involved in heated arguments over how to analyze these tables. I'm reasonably certain that in terms, given that there are only 4 numbers in the 2x2 table, that this has to be the world's record in number of words written per number. Again, in this crowd, you all remember that a statistic is ancillary for a parameter if its distribution is not a function of that parameter. And the conditionality principle states that statistical evidence about theta should be conditioned on any statistic that is ancillary for theta. In the 2x2 table, this marginal success rate tells us very little about what is the odds ratio for success on treatment 1 versus treatment 2. And for that reason, Fisher felt that it should be treated as an ancillary statistic, and hence Fisher's exact test is based on the hypergeometric distribution of y1 given the marginal success total. Controversy arises, at least in part, because y plus is not a perfect ancillary statistic. Hence, we need to gauge how much information is lost if we, in fact, do condition on y plus. Is there a quick way of getting getting back to the PDF version of? No. Okay. Well, again, never ever use Microsoft. It's some of us are slow learners. I'm particularly slow in this regard. Its ability to do font substitutions on you is really hard. However, my one backup is at least some of you have my handout, which in fact, so you'll need to guess. But anyway, we can parameterize these tables as pi1 and pi2 being the probability of success on these two different treatments, and we can reparameterize this as psi being the log of the odds ratio for success on treatment 1 compared to treatment 2, and lambda is the marginal probability of success among all treatments combined. So if we do this, then psi becomes the parameter of interest, and lambda is a nuisance parameter. So we can rewrite the likelihood function again. This is psi, and that's supposed to be lambda. Be a spot quiz at the end of the talk if you remember what these things are. But the full likelihood of for psi and lambda, given the observed number of successes, is going to be proportional to the marginal likelihood for lambda given the marginal total times the likelihood for psi given y1 conditioned on this total. Life would be a lot easier if this likelihood was not a function of psi, because then it really would be an ancillary statistic, and the arguments for conditioning on it would be extremely strong. As it is, if we're going to use the conditional likelihood, we need to gauge how much information is lost by doing this. And so, to give you a number of examples, starting off with 10 patients on each treatment with one success in each group, and this is the full likelihood where lighter colors indicate higher values of the likelihood, and then these again, this is the full likelihood. This is the marginal likelihood, and you'll note that if you hold lambda constant, that this likelihood is extremely flat, suggesting that there is really very little information here about psi. The relationship here, these colored horizontal lines here show the actual values of the marginal likelihoods, and so for example, if you take this value here, this is equal to the conditional likelihood here at 0, which is this value, times, say, the magenta curve at 0.06, giving you this value here. And so the key point here is that really there is very little lost in basing your inference on the conditional distribution, the conditional likelihood being virtually identical to the profile likelihood. This is a similar example, again, keeping the number of patients on each treatment constant, and again, you get very much the same result. one of the reasons why the marginal success rate isn't completely ancillary is that if you know what the marginal success rate is, then that means that y1 has to take a value between 0 and 6, and each of these values is associated with an estimated odds ratio. But you'll note that these potential estimates are symmetric about 0, and they're the same number of ones favoring a negative log odds ratio as there are ones favoring a positive log odds ratio. So there's really very little grounds, or very little is lost by conditioning on the marginal total. Things get slightly more interesting. Well, yeah, and this again tells you basically this same picture with the marginal likelihood with the conditional likelihood being very similar to the profile likelihood. Things get somewhat more interesting when the number of patients in the two different groups differ, and now the marginal likelihood surface isn't completely flat. And the reason for that is that that given that we have, let's say, a total of 3 successes, that means that there are two possible outcomes associated with a positive log odds ratio and only one associated with a negative one. However, in spite of that, so this is the corresponding series of graphs, but in the area where the conditional likelihood actually has real values, positive values, there is really very little going on here, and once again, the conditional likelihood is very, very similar to the profile likelihood, or for that matter, the likelihood obtained through this transit here at the maximum likelihood value of lambda. A more pronounced example is given here, where again we have 10 versus 20 treatments and a total of 11 successes, and now there are 7 values, possible values of the log odds ratio estimate that are greater than 0, as opposed to 4 that are less, which explains why the marginal likelihood surface here is actually quite a bit higher out here than it is down here, as is indicated here. However, by the time we get to this region here, the conditional likelihood is in essence 0, and so that overwhelms this difference here, and once again the difference between the conditional likelihood and the profile likelihood is extremely small. Looked at another way, this is showing you the profile and conditional likelihoods. For the first example, there really are no differences whatsoever. For the second, the conditional likelihood is pulling the maximum likelihood estimate slightly towards the null as compared to the profile. But again, the differences are extremely slight. And the same is true for the fourth example that I showed you. All of which leads us to the conclusion that it does indeed make sense to condition on the marginal total. However, that being said, Fisher's exact test is still too conservative due to the limited possible outcomes of the conditional distribution of y. So, for instance, in this example here, there only are 7 such values. This leads to large probability masses for many of these values, which in turn leads to the Fisher's exact p-value being too large. As opposed to if you look at all the outcomes, there are a whole lot more of them. They're much closer to a continuous distribution. So what to do about all this? Well, as true blue likelihoodists, what we would first of all recommend is that you report likelihood ratios with the appropriate support intervals. If, cruel world that it is, and someone mentioned about the 80% of the frequentist statisticians out there, but if referees and editors bully you into publishing p-values, the one that we recommend is the likelihood ratio chi-square statistic based on the conditional distribution. So we're comparing the likelihood under the null versus the maximum likelihood value, which sort of has a chi-squared distribution 1 degrees of freedom, although we recommend this not because of the chi-square property, but because of the fact that this p-value is a monotonic function of the conditional likelihood ratio, and hence it will be inferentially consistent in the sense that if you have a normally distributed statistic with the same likelihood ratio as what you're getting out of your 2x2 table, the p-value for the normally distributed statistic will be identical to the statistic, the p-value you get here. So it is, if you will, it's a surrogate p-value, surrogate for likelihood ratio. You might even think of it as a stealth p-value, in that you can give this thing reference Choi et al. And all those likelihoodists, or all the frequentist referees, they're going to remain asleep, and they aren't going to realize the heresy that you're actually trying to stick in here. So at any rate, Lena Choi has an R package that will calculate this and all sorts of other relevant statistics. And we also have a RStudio Shiny app that's, again, it's in the handout, or you can find it on our webpage, where you can stick in these numbers and get the appropriate p-value of your choice. And so thank you, and thank you, Chuck, for all of your mentoring. I also have stories of Chuck picking me up off the ground, but in the interest of time, I will not.